right. So good afternoon all. I hope you had great vacations, but it's time to study now, start the studies. So this is the first class of your 12th lecture, right? Okay. So today we'll start with electrostatics. I hope you all remember a fair bit of mechanics, because mechanics is one topic which will be used everywhere. Questions will be mixed with mechanics. So even in JEE, mains or advanced both, questions directly from electrostatics would be there, but also mixed questions, mechanics as well as electrostatics. So just a second. Okay, so this is electrostatics. What do you mean by electrostatics? Study of charges at rest. So right now in your schools, as far as I know, chapter 6 may be running. Electromagnetic induction. Fair? On 4th. In most of the schools, chapter 6 is running by now, actually 5th or 6th. Fair enough. So you all have studied the basic properties. I would discuss them in very brief, so that we can discuss more the JEE related stuff, right? So I would be, for all those discussions, all those derivations which are in NCERT, I would be taking very small time. Is it okay? So that we can progress more towards the JEE thing. So in case you have any doubt in any derivation of your NCERT, you can ask. I'm saying this to the online students as well. They can ask straightforward. Okay? Otherwise, I will be rushing through all the NCERT stuff. Is it okay? So the plan would be like this. We would be discussing a little bit of charge, a little bit of Coulomb's law, more of superposition principle, because it's the tougher part, right? Especially the continuous charge distribution based systems. And we would discuss electric field. That's the plan for today. I'll try to finish things till electric field. Okay? So let's start. So charge. What is charge? Property of matter due to which it has electric and magnetic properties, right? Electric and magnetic interactions. So you know the properties of charge. This is property of matter. I won't be writing it. Its properties. It's a scalar, first of all. It has two types, but shows algebraic addition. So it's a scalar. Then conservation. Yeah, conservation. Additive actually is taken care in scalar thing. So quantization. Anything else? Any other point? Nahin? Two types. Two types. And one more thing which is actually not very important for you. It is, yeah, it's relativistic invariance. What I mean by that is that as you increase, as you move closer and closer to the speed of light, your mass increases. Einstein in his special theory of relativity said that mass of a moving object is this. So as you as you increase your velocity, the mass increases, and when you reach c, when the speed becomes c, mass becomes infinite. However, charge, this is called relativistic variance of mass. Mass varies relativistically. Okay, charge never shows this kind of thing. Okay, so this is relativistically invariant. So a quick question on quantization, because rest all are like okay, theoretical stuff. So a question on quantization is this. A boy walks on a carpet wearing socks. His body gathers a charge of 2 microcoulomb. Find the number of electrons transferred. Right? For quantization, you already know Q is plus minus NE.
2 into 1 10 to the minus 6 upon 1.6 into 10 to the minus 6.
So it's pretty straightforward. The charge is 2 into 10 to the power minus 6 is N.
1.6 into 10 to the power 19 minus 1.
Right? So N can be calculated. Obviously, I won't be doing it. This for you to take care of. Right? Can I erase it? So the next topic would be Coulomb's law. That's all what we discuss. You know, there are charging methods as well. I'll explain them verbally. I won't be writing anything. Charging methods. You know, there are two charging methods, two ways actually. Charging of insulators and charging of conductors. So for insulators, friction is the only way. Whatever work you do against friction helps in transfer of electrons from one body to other body, right? You already know a lot of examples for this. And that's how electricity was first discovered in Greece, right? So the next way is for conductors, and you know, for conductors there are two possibilities. One is charge sharing, which you call conduction. So we would be discussing it, charge sharing. We would be discussing, you know, it in quantitative terms, you know, in formula form. That's when we actually reach capacitors, okay, or at least cross potential. So conduction, whenever conduction happens, the two bodies always have same potential whenever they are put in contact. Is it okay? So we'll discuss this later on. The other method is induction. This you already know, charging by a distance. One charge is kept, the another charge is also kept, then connected to earth and all, right? So let's move to Coulomb's law. Yeah, I'll discuss the points, right? So if there is one point charge, another point charge, it is valid only for point charges. Okay? Valid only for point charges. So if this distance is r, Coulomb said that force of interaction is
Square of
directly proportional to product of charges, inversely proportional to square of distance. So we write this in this manner. Additionally, we write this in this form as well. Okay? K is called electrostatic constant. This is permittivity. This is electrostatic constant. The value is 9 to 10 to the power 9, and is it okay? The units? Newton meter square per Coulomb square. Epsilon, this is called permittivity. Double T. Of free space or vacuum. Not air exactly, it's just that air has almost same value, so we treat it in a similar way. The value for it would be 8.85 into 10 to the power minus and the units
Newton.
exactly inverse of these, Coulomb square per Newton meter square.
What is the meaning of this condition?
I'll just brief it slightly. More would be coming when we study dielectrics. So right now, let's study let's understand what is permittivity slightly. What happens when you place a charge in vacuum? There is no medium particles. There are no medium particles. Nobody is around here. So that's a different story. Let's say we keep it in HCl, liquid HCl. Is it okay? It is a very simple atom. That's why simple molecule, right? Water has two bonds, so it's a little difficult to treat. I'll assume that we have kept the charge in HCl. Is it okay? So what happens? An HCl molecule is something like this. Oh, sorry, ulta. Negative here, right? I can say it has two poles, right? It is a polar molecule, right? Two poles, positive pole and negative pole. So if the charge is positive, what happens? This kind of alignment happens. Right? What exactly have you done? You have spread the effect of this small concentrated charge to a bigger sphere. So these inner areas, they are now experiencing lesser force, right? You can say some part of this charge is neutralized by the effect of these partial negative charges. So effectively this positive charge is now less strong, it creates lesser field. So effectively, charge is conserved. What has happened? Some part of the charge has spread over to the surface. So if you have a spherical container, okay, and you keep the charge at center, what happens? The charge spreads to the surface. Okay, so anything kept in the sphere, in the spherical container, will now experience less force. This effect is this spreading of charge is indirectly a consequence of permittivity. Okay, what I mean to say is that a medium with higher permittivity has more capability of spreading the charge. Metals have infinite permittivity, means they can spread the charge instantaneously, completely. Is it okay? You keep a charge in a metal, it goes to surface. So anything kept in the metal will not experience any force now, right? So permittivity is nothing but this spreading charge, the property due to which a medium spreads charge to the surface.
So that means charges will be more sterilized on metal surface.
Charge will be more stabilized, exactly.
So but
Yeah.
the negative will repel each other.
No, but actually these are partial negatives.
Okay.
Okay, so the repulsion between them would be far less as compared to the attraction by this strong positive charge. Is it okay?
So if the effect of this charge is neutralized by these partial negative charges,
Mhm.
then its effect will also get decreased on the outer, like the charge which is outer surface also will decrease because of the.
Not exactly. See, you already understand this, that people coming in late. You already understand this, that the total charge, the medium was neutral, right? The total charge of the system would be conserved. What you have done is that out of, let's say, 10 Coulomb charge, you have spread 1 Coulomb charge to surface. Okay? It's still 10 Coulomb here, but all these negative charges, they form -1 Coulomb. So these -1 Coulomb charge, they effectively neutralize, reduce its value to 9, while +1 Coulomb charge is now transferred to the surface. This is not exactly happening. It's like because of the alignment of molecules, right? It's because of the alignment of molecules. So anything which is kept here will only experience charge because of 9, not 10. You can understand this as +10 and all these as -1. So effectively this any particle kept here would experience a charge due to +9 only. However, if anything is kept outside the medium, it would still experience a charge because of +10 only. There is no reduction in charge. I am not neutralizing, I am not destroying any charge here. It's just that inside the medium effect is less, but if you keep another charge outside the medium, it will still experience the same force if the medium had not been here, as if the medium had not been here. Is it okay? It would still experience the force because of 10 only. Is it okay? So while this epsilon naught comes in picture, it comes in picture when both the charges are kept in the same medium. If they are kept in different media, then we need to rethink on this spot. Is it okay?
So,
Yeah.
why the Coulomb's law is applicable only for point charge and stationary charges?
I'll explain. Don't worry. Hold. Is it okay right now? So far so good. Can I erase it?
Yes, sir.
Okay. Okay. You are writing. So please note that when dielectrics come in picture, we need to discuss it once again, even in even more detail, the effect, the role of dielectric. So this topic would be touched again. Is it okay? If you want to write, you can go ahead right now. Not an issue. I hope I can erase this.
Yes, sir.
Some of the properties of this charge, this force, okay, properties of force or important points for this force. Important points. One point we already discussed, the role of medium, right? Okay, one point we already discussed, that K is 1/4 pi epsilon naught, and this is permittivity. Yeah, the role of medium. Okay. The other thing, electrostatic force is a conservative force. I'll try to connect you to the work energy chapter. For conservative forces, we know that round trip work done is 0 always, right? And work done against conservative force is stored as potential energy. So potential energy thing is defined only for conservative forces. We don't say potential energy due to friction. Why? It's non-conservative. Even magnetic force is non-conservative, and we don't say magnetic potential energy. We don't use this term, right? So work done against F conservative is equal to delta U, change in potential energy. Is it okay? Energy conservation valid. Okay? If only conservative forces are acting. Third, these are central forces. Let me tell you what I mean by central forces. This is a very important point. Yeah. This is point charge Q1, this is point charge Q2. Okay? So force on Q2 is acting toward this point. If I move the point Q2 here, it will still act toward this point. So if Q2 completes one circle, the force would always be acting toward a particular point called the center, right? If Q2 completes one circle, force would always be acting towards the center, which means if I take this point as reference, angular momentum about this point would always be conserved. समझ आया? नहीं? ऊपर से गया? है? Let me tell you. This force is acting toward the center. Okay? Now you are sitting at this point and you want to find torque of electric force about this center. What would be the torque?
Force into perpendicular
I
distance.
think torque भी revise थोड़ा सा कर लें,
Yes.
right? This is the body, this is your reference point, and this is the force. So torque is like
Force into perpendicular distance.
either it is R cross F, or in simpler terms, I'll just a second. This is the reference point. Let's say the force acts in this manner. This is your R vector. This is the point of application of force. Okay. So this is reference point. Okay, and this is this here is point of application. POA I would say. पूरा नहीं लिखूंगा. Is it okay? So torque you already know was R cross F, or it was extend the line of this force, drop a perpendicular. This thing is called R perpendicular. Okay. So instead of taking all this, you can directly write force as R perpendicular into force. Force into perpendicular distance, and the magnitude you can find using this concept. You know, place a rigid body from reference point along R perpendicular, right? I'll explain it this way. Place a rigid body. You have a pen or marker, it's fair enough a rigid body, right? So place a rigid body here along R perpendicular, and you know, fix it at reference point. Now apply the force F. The rotation is in what direction? Anti-clockwise. I have a watch, I check it. You know, the rigid body is rotating from 6 p.m. to 3 p.m. right? So that's the sense. That's how you find the sense. What if the force, this is your reference point, and the force is acting here like this. If you extend the line, it passes through the reference point. What in this case? Since R perpendicular is 0 in this case, right? R perpendicular is 0 in this case, torque would be 0, right? Let's check the thing here. The force passes through the center always. This is what I mean by central forces. A force which passes through a center, it means about this center the torque would always be 0. So what I mean to say is torque because of electric force, is always 0 about center, and when torque is 0, you know, angular momentum is conserved, okay, which means angular momentum is conserved about C. Now you would be asking, why am I bloody going into this angular momentum, torque and all? Why? Because you know, years after years they have asked one favorite question of theirs, which is the stopping distance. You have a fixed charge, you project one charge toward the fixed charge, it stops. That was one form of the question. Another year they asked this, that okay, this one is also moving, this one is also moving, this is free to move, this is projected. So as it comes closer, this one starts moving, okay. So what if they, you know, call it two protons are kept like this, one proton is kept like this and another proton is projected. So you may think that it's a modern physics type of question, you know, nucleus ka kuch. It's not, it's electrostatics. On another year they asked this. This is a fixed charge, another small charge is projected like this, not along the charge but like this. What happens? Because of repulsion, this gets deflected. Now they asked, what is the minimum distance? How to go with this? How to go for this? Central force. This electrostatic force is central force. So torque will be 0, angular momentum will be conserved. That's the only line of attack you got in this kind of question. When there is change in direction, linear momentum won't be conserved because direction change hai. Okay, only angular momentum would be conserved, energy would be conserved always. Okay, so don't worry, we would go in there, but it would be after we study potential energy. So that's why I am discussing all this central force and all theory. So please pay very good attention to these 2 points, second and third.
Sir, how can we prove that this is a conservative force?
How can we prove that this is a conservative force? Okay, actually, central force itself has this kind of concept. When you take it along any path, okay, when you take it along any path, what happens for some portions, since the force is central, I'm not saying that it's going in a complete circle, just think about it. This is one charge q1, you take it along any path. Since force is always central, for some portions angle would be 90, for some portions it would be acute, but for other ones it would be obtuse. So work done for some portions is positive, is negative, for some is 0. Okay, it would definitely be conservative. It would definitely be conservative. Is it okay? Experimentally it can be proved. I hope you all have written this. अभी नहीं हुआ, जल्दी, hurry up. हो गया? I hope it's done. इससे ज़्यादा टाइम हमारे पास नहीं है. We cannot write leisurely. You know what? Even gravity is a central force, conservative in nature, and even for gravity, the same kind of behavior is observed. What? Angular momentum is conserved. That's why Kepler laws were derived. You know, Kepler laws were derived. So it behaves in quite a similar manner. Electrostatic force behaves in quite a similar manner. Okay. In fact, gravitational field lines do exist, just like electric field lines. Okay, and everything. So you can use same concepts here and there. Okay, similar approach is required. So it doesn't matter, the question won't ask you compare this to this. It would directly ask you either the gravity thing or the electric thing. So the approach to solve the problems is quite similar. It is just that gravity is only attractive. So only one point you need to take care of. Okay, otherwise behavior is quite similar. So we had 3 points. The fourth one, attractive repulsive nature. Okay, attractive repulsive nature and all. Okay, this is a field force. So a charge produces a field around it, which we will discuss. So it would be attractive as well as repulsive. So no other special points as such. No other special points as such. The next thing which we should discuss is superposition. ठीक है. What is superposition principle? Anyone?
Yes, sir.
What is it?
According to this proposition, the force acting on a charge is the vector sum of all the forces acting on that, and the
Individual forces
are not
affected by the
affected by
presence
the
of other charges.
Exactly, exactly. So text. Okay, so I'll write bigger. I guess I'm writing a way too smaller. So this would be superposition principle. Right. So what is the need of superposition principle? We will discuss. Okay. First we will discuss superposition principle. Then I'll take your query that why it is valid. Coulomb's law is valid only for point charges. Why? Is it okay? So superposition principle, it says that, let's say there is one charge q and we have collection of charges q1, q2, q3, q4. So q1, because of q1 there is repulsion, because of q2 there is attraction. Okay, q4 होना चाहिए था, sorry. q4 attraction, repulsion because of q2 and attraction because of q3. So this, due to q1 let's call it f1 vector, due to q4 it is f4, q2 f2, due to q3 it is f3, vector, vector, vector. So the net force on q1 is vector sum of
all the charges.
vector sum of individual forces because of all the charges. So what I mean to say here is that, take this pair, find the force between them, imagine no other charges there. Okay, so you'll get f1 this way. Take this pair, forget any other charge. Okay, so what you would get? f2, similarly f3, f4, right? Take vector sum. Okay, it indirectly means that if I remove q3, f1, f2 and f4 would not be affected, however the total force would be affected, obviously it would change. So if I remove f1, remove q3, sorry, means f3 is no more. So f1, f2 and f4, they are same. I don't mean same means equal, I mean they remain same, exactly same value, right? So they remain same. I'll write bigger, sorry, somebody should remain same, right? Okay, while f net या फिर f q1, f net or f q1, it will definitely change. It will definitely change. Is it okay?
So
Yeah.
Q3 will repel or attract the other charges. So
Q3 will,
the
yeah, huh?
so why we are saying this thing like
Right now, sorry, not q1, q only. Right now I am concerned only with forces on q1. It is possible that there may be one force like this, one force like this. I'm not concerned with them. I want to study only q. That's why I'm taking forces only acting on q. Is it okay? I'm not concerned with the forces acting on q1, q2, q3, q4, right? Okay. So you have to select the charge on which you need to calculate force. When you have selected it, बाकी सब के लिए you need not pay attention to the forces. For all others, you need not pay attention to the forces, right? Is it okay? So shall I erase it? Okay. Let's take a few examples. Let's take a few examples, and first take easy examples of direct Coulomb's law. Then for superposition, then we'll move forward to continuous charges. This is for discrete charge arrangement. Discrete means one charge here and there. Okay, the charges are not filled everywhere. It is one here, one there, and so on. Discrete. So this is for discrete charges. What I discussed, I'll discuss for continuous as well. So shall I raise it?
Yes, sir.
So the first question says, anyone asking a doubt? Yeah, somebody asked that will not, please can I please somebody asked that will not a force of attraction or repulsion between other charges affect the net force? Okay, so net charge वहाँ लिखा है, it's net force. So let's say again I'll repeat, this was Q, Q1, Q2, Q3. Okay, so between Q1 and Q2, let's say this is the attractive force F1, because of Q2 it's F2 repulsive, because of Q3 it is again repulsive, right? I am right now concerned with force on this. There may be a force between these two charges, but I am not paying any attention because I need force on this. In every force calculation, one charge should be this one, right? Okay, my important charge is this one. I need forces on this. So maybe others are experiencing force as well, but they are not my point of concern. So similarly, the forces between Q1 and Q is not, this F1 force is not dependent on what force acts between these two charges or these two charges, right? Okay, it does not depend at all on what other pairs experience. It only depends on what is the two charges and the distance between them. बाकी सब भूल जाओ. Is it okay? You can ignore them. So let's start with the question. The question says, let's say this is a charge minus Q1 fixed, okay, another charge Q2 is revolving around it in a circle of radius r. Okay, a charge Q2 is revolving in a circle of radius r. The mass of particle you can take m. Okay, mass you can take m, mass would be needed, right? So in a circle of radius r, okay, around a fixed charge minus Q1. I hope I'm writing big enough. For you it's okay. I'm asking the online people. Okay. Okay. The charge, is it okay?
Yes.
So another this charge, positive charge, is revolving around a negative fixed charge in a circle of radius r. So you need to find the velocity rather speed. Velocity is changing, so let's not write velocity. Speed of q2. Okay, a particular speed would be there. If speed is less, the orbit size would decrease. If speed is more, orbit size would increase, right? And time period. Just tell me quickly.
So we will take centripetal force
Yo, exactly.
and we should. Sure.
Yes.
V square.
mv square by r. What? Yeah, exactly. m नहीं होगा, r स्क्वायर होता है, k q1 q2 by r स्क्वायर. एक ही तो कैंसिल होगा, r स्क्वायर होता है ना, एक ही तो कैंसिल होगा, mr. So exactly, and time period, what would be the time period? 2 pi r by v. Is it okay? Done. So let's discuss. It's an easy question. Okay. So this charge will experience an electric force which will act as centripetal. Okay. Okay. This is the correct statement. I won't say it would Q2 will experience a centripetal force. Centripetal force is not a real world force, I tell you very clearly. Okay, it's a pseudo force, it's a nakli fake force, right? Okay, so any force which causes circular motion of a particle is centripetal. Getting my point? Centripetal is not a real world force. What we do, we label any force which acts towards center as centripetal. Is it okay? So here electric force, yeah, the answer is correct. नहीं, minus sign नहीं होगा.
So they are
Sir,
substituted
minus
with
Q.
sign.
Okay, okay. But actually, we need not do use the sign here actually. The sign, negative sign indicates that force is attractive. Let me solve it for you. Electric force would be K Q1 Q2 by R square with a negative sign. Actually, it would be like this. But the negative sign indicates that force is attractive. So you need not use negative sign because you have already taken the direction as attractive, right? Is it okay? If the value of force is positive, it means it's repulsive in nature. If the value is negative, it's attractive in nature. So when we have already shown in the diagram that force is attractive, then we need not take negative sign. We can take only magnitude. Is it okay?
So will it be wrong if we are using negative?
Actually, in root there would be a negative sign, which means it would be a complex number. How can a force be a velocity be complex? How can a velocity be complex? So what I would be doing, I would not be using this directly. I would be saying that electric force is KQ1 Q2 by R square. I'll only take the magnitude, and it is equal to centripetal force. Why? Because electric force acts as centripetal. Okay. So now solving it, we would be KQ1 Q2 by MR under root, and time period would be 2 pi R by V. You can find it. Okay, you can find it. So shall I erase it?
Yes, sir.
another one, this is coordinate system, a charge q1 is placed at position vector r1, another one q2 is placed at position vector r2. Okay, so find electric force in vector form. Okay, you can assume both are positive. Find electric force in vector form. How to approach it? No. No charge is kept here. Only two charges are there. The separation between the charges would be how much? You can take r2 vector minus r1 vector or r1 vector minus r2 vector. Okay. So I'll erase. Let's check what's the difference between the two possibilities, r1 minus r2 or r2 minus r1. r2, this is r1, let's call this delta r. Okay, okay, so r1 and delta r add up to give r2. This you already know, r1 vector plus delta r is r2 vector. So delta r would be r2 minus r1. So from delta r is from r1 to r2. Okay, if I take it in the opposite sense, r1 minus r2, it would be from q2 to q1. So right now I'm taking the direction as this. So force on q2 would be in the same direction. Is it okay? Let's try to find the magnitude first. Force on 2 would be k q1 q2 upon r2 minus r1 mod का square. Okay, okay, the length, this is delta r vector, so iska length, we need the length only, length ka square, and the direction would be along delta r. So you take directions only according to what? Unit vector. Yeah, obviously positive, but you take directions only according to unit vectors in these scenarios. So the direction would be delta r cap. Is it okay? This is the force, this is the direction, and delta r cap would be
R vector upon R.
So it would be delta r vector upon delta r, or r2 vector minus r1 vector upon r2 vector minus r1 vector mod. Right? Okay, so this would form a cube in the denominator, k q1 q2 by r2 vector minus r1 vector mod cube, and this is r2 vector minus r1 vector. This is for f2. For f1 it would be inverse, r1 vector minus r2 vector. Is it okay? For f1 it would be inverse. Okay, so instead, if in case r1 and r2 are not given in this format, they are given in numeric ways. Like the charge is kept at 1 comma 0 comma minus 1. This charge is kept at 2 comma 3 comma 4. So what would be R1 in that case? It would be I cap plus 0 j cap minus k cap. For R2 it would be 2 I cap plus 3 j cap.
J cap plus 4K cap.
So you can still use the same thing with new values. Is it okay? Is it okay? So it is like pretty much NCRT type of thing, not very difficult. बढ़े आगे? Shall we move? Shall I erase it?
Yes, sir.
अच्छा, अभी some of you are writing. कर लूँ? Erase कर दूँ? Right? Erase करूँ? तो कर दूँ यार. कुछ तो घर के लिए भी छोड़ दो ना. You know, some calculations are to be done at home when you are revising. Okay. Now these were plain and simple Coulomb's law questions. Let's discuss some questions on superposition. Is it okay? Have you done logarithmic series? Logarithmic series? नहीं किया होगा? नहीं किया होगा. चलो कोई नहीं. Nevertheless, okay, one charge minus q is kept here. Now this time we have plus q and plus q. All these charges form an equilateral triangle. The radius of the circle is r. Is it okay? Whole of the arrangement is revolving. This charge is fixed. This is moving like this, this is moving like this, this is moving like this. They should move with same speed, otherwise, okay, this arrangement will not will become unstable. Is it okay? This time you need to find v. Find v. Okay, or this time this would be an equilateral triangle. Charges form an equilateral triangle always. Okay, plus q charges, I should say. Negative charge is fixed. The plus q charges, they form an equilateral triangle always. Again it would be centripetal, but you need to find the net electric force. This would attract, let's say we are planning to find a force, let's say on this. So the negative charge would attract it in this direction, while this positive would repel it away. Even this positive would repel it away. That force may be, net force may be 0. May or may not. The distance is less, here the distance would be more. So अभी कुछ कह नहीं सकते, you cannot say anything until you calculate it. Net force 0. Are you really sure? What would be the length of side? What would be the length of side? कितनी होगी? See, for this equilateral triangle, this is the circumcenter and this is the circumcircle and R is the circumradius. So you know circumradius is how much? A upon root 3. This is side A. ऐसा ही होता है ना? This is what I remember. You know, maths. This is what I remember. So A would be R root 3. This would be R root 3. Even this. The angle here is 60. So between these two forces, the angle would also be 60. Right? So let's try to find the force. Yeah, first let's find the attractive force. Let's call it F1. The F1 attractive force would be kq square by r square. I'm not taking a negative sign because here I am taking the directions. Negative sign is only to show you the direction, but since I have taken the direction correctly, I need not take negative sign. Okay? Is it okay?
Yes, sir.
So F1 is like this. F2, the repulsive force would be kq square by r root 3 whole square. Okay? This is same as F3. Right? So net repulsive force, you know, a combination of these two forces.
F1, F2 का whole square plus F3 का whole square plus 2 F3 F2 complement.
Let's call it, since the two forces are equal,
So F
let's call them F under root F2 square plus F3 square plus 2 F1 F2 cos theta, right? Sorry, F2 F3. Okay, or I can simply write F square plus F square, because they have equal magnitude, 2F square. Angle is cos 60. Cos 60 is half. So it would be 3F square under root of 3F square, or root 3F, or root 3 kq square by 3r square. Right?
yes sir.
So, you know, I have very less space. I have only this much area. So let's find the net force. Attractive force is this, repulsive force is this much. Is it okay? So net force would be kq square by r square minus kq square by root 3r square. Is it okay? Net force is attractive. The attractive force is stronger, repulsive force is weaker. So net force would be toward the center, and this would provide mv square by r, the centripetal force to this charge. Is it okay? You can find v. It would not be a happy expression, but you will still get the answer. Is it okay?
Yes sir.
Okay. The answer would be, कहाँ लिखूं? Can I erase the diagram? नहीं. I'll erase the top part so that, you know, I can write the answer.
Root 3 minus 1 upon root 3r into
Yeah. mv square by r was kq square by r, 1 minus 1 by root 3, r square, sorry, 1 r would cancel. V would be kq square by mr under root 1 minus 1 by root, sorry, bracket 1 minus 1 by root 3 whole under root. So not a very happy value, but still the answer. Is it okay? So if the values of k, if the values of q, m and r are provided proper values are provided, you may get an integer answer out of it as well. Okay. So it's a previous year JEE problem. It's not, it's like way back, it was asked way back, but it's a previous year JEE problem. Is it okay? Shall I raise it? Okay, I hope everyone has written the answer as well. If not, you can still visit the video, right? Okay, another one on superposition once again. Okay, we won't be discussing, these are for discrete charges. So as you know, over the years, the flavor of JEE questions changes. So it's not in flavor right now, okay? But you may find one or two questions here and there in state level exams or something. So I'll give one more question, then we'll move on to the continuous charge distribution. That's a lot more important. So let's discuss. 6 charges are not 6, 5. Five charges are kept at corners of hexagon, and the side of hexagon is L. This is the center. Is it okay? Side of hexagon is L. This is the center. 5 charges. This is empty. Rest all are Q, Q, Q. Okay. You have only one charge at center. One charge at center, which is small q, negative. What would be the net force on this charge? What would be the net force on this charge? You can. What are you doing? I'm shocked. It's straightforward. No, don't you think so? It's pretty straightforward. You need not calculate. Verbally hoga. It's a regular hexagon, as I said. The figure may not suggest it, but it's a regular hexagon. And a regular hexagon is nothing but 6 equilateral triangles placed together. So every inner side would be L as well. The force between these two is cancelled by the force between these two. These two forces would cancel here and here. These two also would cancel each other's force. Only this would attract our charge in this direction. So only one force, that is KQQ by L square. Khatam. That was the answer actually. I was expecting you to be very quick in this. Symmetry, nahi? Okay. So in all the regular figures, I was planning to give this question in a square, but square, in case of square, you would have what?
Q square upon something. We have to show the diagonals and something like उधर भी होगा force और diagonals के ऊपर.
हाँ. Square के case में is very easy to pick this up. Very easy. कि अच्छा दो तो cancel, force due to 2 would cancel out, and only force due to 1 would be there. One corner is empty. So that's why I gave hexagon. I thought maybe you would still pick up, but no. Why? Bad. This is just the beginning. Let's have a proper question now. two charges are kept at some separation. I will increase the separation here as well. Are kept at separation 2L. This is center. Okay. I will draw a line. This is what? Equatorial line. You know equatorial line? Dipole you have already studied, right? So this is an equatorial line. You have kept a small q charge here. Obviously the small q charge, it's a negative charge. Obviously this negative charge would be in equilibrium at this position.
Yes, sir.
Right? Okay. So we would be discussing equilibrium separately, you know, after energy. Is it okay? Because it needs energy discussion as well. So right now, just try to understand this. This is understanding the equilibrium is very easy. The question is something different. A small q charge is placed at center. Okay, it would be in equilibrium. Now it is displaced through some distance x. Because of the forces on two charge due to two charges, fixed charges, it would try to come back. So it would actually oscillate. It would oscillate up down, right? Is it okay? So my question is, how much would be the time period of those oscillations? Okay, how much would be the time period? That's a proper question actually. These were like easy ones. Okay, and we would be extending the concept to 3 charges, 4 charges, even a hexagon. You would be able to apply the concept even for a hexagon. Is it okay? Okay, let's discuss now. So I would be solving it, don't worry. Okay, chinta mat karo. Let's discuss now what's happening actually. I hope थोड़ा बड़ा मैं लिख देता हूँ so that this distance is x. Okay, and this would again be x. It would oscillate like this. Okay, so the statement is a small particle of mass m and charge minus q is placed midway between two charges, two fixed charges, two fixed charges, okay, plus q each. It is now displaced slightly from its slightly along equatorial line. Find its time period of oscillation. So how to approach it? Let's check this out. Okay, let's say this distance is x, this is L, this is L, midway tha, is it okay? So now this charge minus q experiences attractive force because of this plus q and the other plus q as well. Let's call them, they would be equal, is it okay? They would be equal. So let's call them F. The hypotenuse here would be x square plus L square obviously, right? So force F would be k q small q upon the distance r square, which is k q q upon x square plus L square. right? X square plus L square. The other would be as such, similar. Okay, let's say this is the component, this is the angle theta, angle between the force and the equatorial line. So you can see that the horizontal components would cancel each other while the vertical components would add up. So we need to consider only the vertical components. So net force would be F cos theta twice of it, right? So cos theta for this triangle would be how much? Base, which is x upon hypotenuse. So it would be 2kqq upon x square plus L square into x upon, right? Okay. Okay. So this is 2kqq, right? Okay. If the particle has mass m, this net force would provide some acceleration ma. So this is the acceleration ma. Is it okay? The displacement was in the upward direction while the acceleration would be in the downward direction. There would be a negative sign. Is it okay? There would be a opposite direction scenario. So the magnitude would be like this, but if I write it in the vector form, it would be something like A vector is minus 2kqq upon m x square plus L square 3/2 into x vector. Is it okay? Why? The acceleration is in the downward direction while the particle was displaced in the upward direction. Since there is opposition, so I am using a negative sign to indicate that acceleration is opposite to x vector. Now you know x is very small compared to L, means x square plus L square is more or less L square. So A vector would be minus k2 minus 2 ml cube into x vector. Okay. Statement, did you write the statement? So you already know that for SHM the condition is A vector is minus omega square x vector. Comparing, you get omega square is 2kqq. Okay, omega is root of this thing, right? And time period क्या होता है? Exactly. So the time period is 2 pi by omega. This is 2 pi under root m L cube by 2kqq. Right? This is the time period. Okay? Yeah. नहीं, देखो, this was the arrangement. दो charges थे. Center में one charge was kept. You displaced it in the upward direction. The displacement is this. And when you release it from here, because of attractive forces, this is a gravity free space. The two charges are attracting it like this. And we just said that actually the horizontal components would cancel, but the vertical components would add up. So these two vertical components would actually bring it back. Is it okay? The charge comes down not because of gravity, but because of these attractive forces. Okay, whole of this arrangement was not vertical, it was kept on a table. Even if it is kept on a table, it would still oscillate like this. So this particle, when it is released, it comes down. So it oscillates like this. सिर्फ गिरता नहीं जाता है, यहाँ आता है, it stops, then goes back. So we are neglecting gravity in this case. Is it okay? ठीक है? So this was a superposition principle question in a right sense, in JEE sense, right? आसान आसान कर रहे थे अभी तक. Okay, you got it? लिख लो, okay? Write it, understand it really well. because we would be, you know, doing a magic here. We would be extending the same thing to 6, 7, n charges. Okay?
So then these six type of questions come in exam. There also we can neglect this.
Exactly. The question said the charge was given a small displacement, slightly displaced. Whenever the question uses this kind of statement, slight displacement, small displacement, okay, negligible displacement, so you can consider x as very small compared to all other distances. So x is very small compared to L, compared to the hypotenuse and all. Okay, I hope it's all done. Shall I at least erase the left half? So now check. When two charges were there, acceleration was this. I'll just write the force as well because it would be handy. Force would be vector sign के हिसाब से minus 2k q by m x square plus L square power 3 by 2 into x vector. Is it okay? The force is like this. I'm using negative sign just to indicate. अच्छा m नहीं होगा, sorry. हाँ, ma. That is A. So, you know, I'm using negative sign just to indicate that this force is opposite to x vector. Is it okay? Just a second. So, ठीक है, for two charges, there were two charges and the central charge was displaced. We had a 2. Imagine another arrangement, okay, and equal 3 charges are kept in an equilateral triangle format, plus q, plus q, plus q. Central charge minus q charge is kept. Let's say the distance is L, this is L, this is L. The central charge is displaced out of the plane. It goes like this, inside outside. Okay? Okay? Another view would be like this. You have kept the triangle like this. The triangle is kept like this, horizontal. The charge is this, and now the charge moves vertically, okay, oscillates vertically. This is the x distance. I cannot show it in this arrangement, but I hope it is clear in this kind of arrangement that central upward and downward direction, okay, upward and downward direction out of the plane, perpendicular to the plane of triangle. In this arrangement, what would happen when the charge is at this position? There would be 1, 2 and 3 attractive forces. We would be taking components, all the 3 would be equal, you understand it, because the charge was at centroid or circumcenter, whatever you may call it, okay. So distances were equal, so all the forces would have same value, they would give same components, the components parallel to the triangle would cancel, while the components along this perpendicular line would add up. 3 components would add up. So the force in this scenario would be minus 3kq and so on. The acceleration would be 3 this thing, 3kq upon this thing. The time period would be ml square by 3kq. So if it's a, you know, regular polygon of 3 corners, so the time period is 2 pi under root ml cube by 3kq. if it's a regular polygon of n sides, n आ जाएगा 3 की जगह. Exactly, that's what I was about, that I wanted to tell you, that yeah, exactly, in place of 2 n would come, right, because there would be n forces, so n components adding up. Is it okay? Is it okay? Okay, just note the L, that L is the distance of not, L is not the distance of, not the side of the triangle, it's the distance of central charge from corners. So even for hexagon, for a pentagon, let's say, this is L, okay, it's not the side length, it's not the side length, it is distance from center of corner. Is it okay? ठीक है? Is it okay? Somebody said, please explain the previous question. I'll explain it. It was a long question. We needed 2 boards for it. At least for whole of the concept, we needed 2 boards. So I'll start from, I'll erase this one. Okay, I'll explain. The question was this. 2 charges plus q were kept like this, another charge was kept at center, the distance was L. Now this charge was displaced through a distance x in the vertical direction, in the perpendicular direction. I shouldn't be saying vertical, it's like perpendicular, any perpendicular direction, okay, and then released. Because it's a negative charge, it would oscillate. Gravity is not present, please note, it's not coming down because of gravity, it is coming down because of attractive forces. So what happens, the minus q charge is here, this plus q charge attracts it in this direction, this plus q charge attracts it in this direction. Is it okay? Somebody is saying something? No, the same thing. Repeat the question. कुछ और भी है क्या? Okay, so the 2 charges attract the forces. Let's call this one as F1, this one as F2. Is it okay? They will be equal in magnitude because the charges are same and the distance between them, it is x square plus L square, it is also same. R is also same in both the cases. The 2 triangles are congruent, right? The 2 triangles are congruent. So F1, F2 would have same value. F1 is equal to F2 is equal to KQQ upon R square, right? From these 2 forces, we would have 2 components, this horizontal one, this vertical one, this horizontal one, this vertical one. The 2 horizontal components would cancel while the 2 vertical one would add up. The vertical component would be F cos theta, theta के साथ cos theta component. It is like this. If this is F, this would be F cos theta. For other force as well, it would be cos theta, F cos theta. So these 2 forces would actually add up. Okay, the total force would be 2F cos theta. Okay, and in this triangle, okay, I'll redraw the triangle because the board is a little dark now. So this is the triangle we are discussing. This is angle theta, this is R, hypotenuse, this is x. So cos theta would be x upon R. So this is 2KQQ upon R square into x upon R. Obviously R would be the hypotenuse under root x square plus R L square. Okay. So the force is directly proportional to x. Okay. whenever force is directly proportional to x and acts in opposite direction, it would be an SHM. You know it by last year's concepts. Okay, so the moment I get force proportional to x, okay, and direction opposite to x, I can say it's an SHM. So to approach, to finally find the time period, you can replace this F net as MA, find A, okay, use the approximation that x is very small compared to L, use the approximation that x is very small compared to L, you can find A and compare it with A is equal to minus omega square x. You get omega, you get time period. Okay, we applied the same concept. This is for 2 charges. Okay, we applied the same concept for n charges because you know, for 3 charges as well. If 3 charges are kept in a triangle and this central charge is displaced perpendicular to the plane of triangle, is it okay? So the triangle is made on the board on a table. We have a triangle on a table, and this central charge is displaced vertically. It would oscillate again. We would have 3 forces, 3 components, and so on. So net force would be 3f cos theta. Then for a triangle, equilateral triangle, net force would be 3f cos theta. Accordingly, the time period would have 3 in place of 2. For n sided polygon, regular polygon, you would have n corners, n forces, n components adding up, and n in place of 2, in place of 2 for time period, right? So we started with 2, but you can extend it. Is it okay? Okay. Tell me, which is the polygon having infinite sides? A polygon having infinite sides? Circle, exactly. What you are doing is you are reducing the size of sides and increasing the number of sides. It would become increasingly round in shape. Just imagine a triangle has sharp corners. What about a square? Lesser corners, right? A hexagon, it is fairly rounded. Octagon, ऐसे चला सकते हो, it's like a football, right? Then as you increase the number of sides, it gets more and more rounded. When n reaches infinity, it would be a circle. Then check out what I would be saying next. You have a ring, the whole charge on the ring is q, have a central charge minus q, you displace it, it would again oscillate, and you can find the time period. Okay, this time, you know, in the expression in what we did, we had nq. In that place, we would be, in its place, we would be replacing total charge. Is it okay? So we would approach it via another way also, but similarly, it can be approached via this approach as well, this way as well.
In case of n, we put infinite.
Actually, if we put infinite, the time period would be infinite. No use then. So in n-sided polygon, the total charge is nq. N-sided polygon. Okay, let's say n-sided polygon. The total charge is nq. Okay, this is the total charge on all the corners. On a circle, the total charge on all the corners is q. We replace nq with q. That's it. Okay, आएगा कुछ time period. Don't worry, it won't be infinite. Huh? We can use that as well. So I would be approaching via that method as well. It's important. Ring is important, right? So not by this, but still, if you don't remember or something.
Because in case of circle, it gets uniformly.
Exactly. Can I erase it? Okay, I hope I have recapped it well. Okay. So that was for discrete charges. For continuous charges, let's say you have one body this, you have one body this, positive charge, here also positive charge. you cannot apply Coulomb's law here. Why? Because what would be the separation? What separation would you take? Separation between center of masses, but they are center of masses, not center of charges, right? Because charge distribution may be different from mass distribution. At least in conductors, we know that if we place two positively charged conductors nearby, the positive charge will move away, right? So what are to take? That's why we cannot apply them directly, and we say that Coulomb's law is valid for point charges only. How to approach it? You need to take small element dq1 here, another small element dq2. The force between them, let's say the separation between them would be how much? Let's take it as r1, r12, right? So you need to find the force between these two. That this would be k dq1 dq2
upon
r12 square. On dq, not only this would apply a force, another charge here would apply a force, here would apply a force. So even on a very small charge, there would be so many forces, okay? And for whole body, you need to find forces on all the small elements. So it becomes practically impossible to find. Okay, it becomes practically impossible to find. So if we have two continuous bodies, we cannot find the force between them. We can find the force between a continuous body and a point charge. It's easier. Is it okay? We would do it in a question. However, if the two continuous bodies have spherical shape and uniform charge density, then they can be treated like point charges. You already know that. We would study it in electric field. So let's do the question which I said, continuous body and a point charge. Is it okay? Erase karo. The question says, this is a point charge and this is a rod. Okay. Rod has uniform charge density. Okay, find force on rod. Okay, how to approach it? You need to find force on rod. Okay, नहीं center of mass नहीं use कर सकते, sorry. I'll tell you why. Okay, center of mass नहीं use कर सकते. Oh, you need to find force. Now what you need to do is finding force on the rod is not that easy as it is for finding force on the charge. Getting it? Charge की position हमें clearly पता है ना, we already know the position of charge clearly. Okay, so we can find the force on charge easily, and the forces, they form an action reaction pair. You already know it, Newton's third law. The forces form an action and reaction pair. So if you find the forces on a charge, you can find the forces on a rod, on the rod as well. Okay. Okay, so to go forward, imagine a small element dx at a distance x. So consider a small element dx at a distance x from q. Is it okay? Now you can check L length has charge q, one length has charge q by L, and dx length would have charge how much? Q by L into dx. This is dq. Okay, so force on q due to dq. df would be how much? Would be how much? K q dq by x square. k q by L dx upon x square, right? मैंने यूनिटरी मेथड लगाया. I applied the unitary method. You already know about unitary method. कौन सी क्लास में पढ़ा था? I said for whole length L, the charge is q, uniformly distributed है. For one length it would be q by L. For dx length it would be q by L into dx. Unitary method. So the total force would be integral df, है ना? Right? Integral df. So it would be k q by L dx by x square. Here x is the variable of integration. The term dx, whichever term has the d thing, is the variable of integration, right? So here x is the variable of integration. The minimum value of x is a. The nearest point element, the nearest element is at a distance a, and the farthest element is at a distance a plus L. So the limits would be a to a plus L. And you know integration far better than me, so tell me the answer quickly. क्या होगा? minus x की power minus 1. Sorry, I accidentally, as I said, you know more integration than me, right? So minus x raised to power minus 1, and this would be 1 by x, right? Minus बाहर ले लो, you are taken minus outside, so it would be 1 by x, and put the limits, it would be 1 by a plus L minus 1 by a. Take LCM, the answer would be KQQ. This. Done? Why we ignore quantization? We are not ignoring quantization. I said, quantization means the charge is an integral multiple of E. I didn't ignore that. Charge would still be an integral multiple of E. dx is not that small case में electron को भी cut करना पड़े. You are not cutting or dividing an electron. dx, the element dx would still carry so many electrons. Okay, it is not neglecting quantization. We are saying dx is small, but it doesn't mean it is very small, so as to carry 1 electron only or 1.5 electron only. Okay.
So, but we used to neglect it macroscopic.
Huh, because the quanta for charge is so small that we don't feel the charge is a quantized quantity. It appears to us that it is a continuous quantity. It's not quantized. It's a completely freely flowing kind of thing. Is it okay? Because quanta, quanta, the packet is very small, right? Point charges, okay, that's a very good question. Point charges mean charges which have no mass, like no dimension. Mass to hoga. Point particles are those which have mass, which have charge, but no dimensions. So even this is not a point particle. This marker spot is not a point particle, it has dimensions. We can use a scale to measure its dimensions, it's 2 mm, right? Okay, but which this simply means that no particle in this world can follow Coulomb's law, because anything which is a point has no dimensions, and every particle in this universe, even an electron, has some dimensions, even though very small. So we cannot use Coulomb's law for any charge in this world. But this spherical the behavior for spherical bodies, this comes to our rescue. You know, for a spherical body with uniform charge density, we can take it as a point charge. So this is a spherical body. Even though it has some dimensions, we can take it as a point charge. Marker spot circular hai, right?
We are taking that point charge at the center of mass.
हाँ.
Then why can't we take it at the center of mass?
देखो, for rod, see, actually it's not like it's my wish, मेरी मर्जी थी कि मैंने for sphere I took the point charge at center, while for a rod I didn't take. It was mathematically derived. It's a very elaborate discussion. It would take up whole 1.5 hours of ours whole. But you can find it in H.C. Verma, in gravitation as well as in electrostatics. H.C. Verma book, concepts of physics. You can find it in that. He has derived the whole thing for you there. Is it okay? And through that derivation, we come to know that actually, okay, the spherical body can be considered as a point charge placed at center of mass. Here, the same derivation won't apply. I'll show you how. What he did for spherical body, he took a small element of that sphere. Okay. So he found force because of all the elements, and he found that it is as good as when a point charge is kept at center. Let's try to find. This is the force in this case. We are not taking a point charge, we are integrating. Let's go for a method B. Let's say instead of the rod, I place whole of the charge at point Q, at center. Is it okay? The distance would be, this is A, this is L by 2. The force between these two would be KQQ upon A plus L by 2 whole square. It is not as good as that, not the same thing. Okay. So while for a sphere the forces came out to be same after integrating, but for a rod they didn't. Okay. No, you said that can we not take this as this charge at center of mass? Can we not take this charge at center of mass? I took the charge at center of mass, this force came, and this is not the force which came via the correct method, integration, right? While for somebody has asked some doubt, I'll explain, don't worry. So while for a sphere, just try to think, for sphere what he did, he found, he took a small element dx, he found the charge on it, he found the force due to that small charge, and he integrated. That force, if let's say this is a sphere, hollow sphere, and charge is distributed over it, this is external charge Q, this is capital Q, the charge on the sphere. If the separation between them is small r, the force that came after integrating was KQQ by r square. After integrating, it came out to be this. So then he could conclude that okay, we can imagine this whole Q as at this point center. We can squeeze whole of this charge at center. Is it okay? So it is only after integration that he concluded this, not because he has come kiya, right? So somebody has asked this, but if two charges of finite dimension placed very far apart can be considered point charge? Exactly. Yes, true. If the distances are very large, then actually they are point charges. They can be considered point charges, right? Is it okay? I hope, okay, the time is up. So next time we'll continue with the electric field and all. Okay, thank you.